I'm here to present about a topic called Analysis of System Security Engineering Design Principles for Development of Secure and Resilient Systems. And my name is Tamale Haman. The student number is 200-12068, and the course is IT Security and Risk Management. I started with an introduction, and the introduction goes, modern systems are complex compositions of system elements, subsystems, supporting elements and systems, and extensive infrastructures that often result in a lot of cyber dependencies, complicated interactions, and emergent behaviors. So they were talking about how modern systems are complex systems. And because of these interdependencies, hardware, software, communications, these complex systems of systems are inherently susceptible to a wide range of malicious and non-malicious events, which can result in unexpected disruptions and unpredictable actions. The US Department of Defense has considered that they cannot be sure their critical mission systems will operate as intended through a wide range of cyber attack by well-resourced nation-states actors. Thus, it is necessary to undertake deliberate systems-level engineering efforts to design, develop, and field secure and resilient systems capable of operating in highly contested operational environments fraught with uncertainty, unpredictability, and attacks from intelligent adversaries, as well as abuse and misuse by humans. For example, owners, operators, maintainers. So this introduction specified the need for system security engineering. Then next was defining what system security engineering is. And system security engineering is a section in system engineering that applies scientific and engineering principles to identify security vulnerabilities and minimize risks associated with these vulnerabilities. It involves the design and analysis to specify, predict, and evaluate the vulnerability of the system to secure threats. Then we went to system security engineering management. And this is an element of the program management that ensures system security tasks are completed. These tasks include developing security requirements and objectives, planning, organizing, identifying, and controlling the efforts that help achieve maximum security and survivability of the system during its life cycle. Then I went ahead to defining additional terms other than system security engineering and system security engineering management. I looked at protection as a capability or statement of the stakeholders' security need requirement, SOC requirement, with the objective of controlling the events, conditions, and consequences that contribute to unacceptable losses. So it is a step-by-step approach to controlling the losses within the organization by stakeholders. Then I went ahead to define the trust as the degree to which the security behavior of a component is demonstrably compliant with its stated functionality. Then trustworthiness implies simply that something is worthy of being trusted to satisfy its expected requirements. Then resilience is the ability to continue or return to normal operations in the event of some disruption, natural or man-made, inadvertent or deliberate. So resilience is the ability to continue operating after some disruption, like a disaster. Then these are the system security engineering strategies. And the first one is access control. Access control provides a conceptual mode of the necessary access controls, i.e. the requirements that must be achieved to enforce security policies. Ideally, realizations of the access mediation concept possess three properties. The three properties are tamper-proof, and number two is always invoked, and number three is can be subjected to analysis and testing to assure correctness. This means that the mechanism claiming to perform access mediation only does what it is supposed to do and can never be bypassed, coerced, manipulated, or deceived. The second strategy is defense in depth. And defense in depth describes security approaches which create a series of barriers to prevent, delay, or deter an attack by an adversary. Typically, defense in depth is achieved through the application of multiple security mechanisms, i.e. conceptual and physical obstructions. It is important to note that implementing a defense in depth strategy is not a substitute or equivalent to choosing a sound security architecture or system design that leverages a balanced application of security concepts and design principles. Then the other strategy is isolation. It is either physical and logical. And this pertains to the creation of separated processing environments. They can be logical or physical or a combination of both of them. While physical isolation is somewhat more straightforward, i.e. physically distinct components and systems. The sharing of data often necessitates logical isolation mechanisms, which requires the use of underlying trustworthy mechanisms to minimize resource sharing. Then the other strategy, and the last one, is resiliency. And this is the ability of a system to perform essential functions in spite of hostile actions. System survivability key performance parameter includes three pillars: prevent, mitigate, recover, intended to reduce susceptibility to adversaries, limit damage from exploited vulnerabilities, and increase system resilience in order to execute the SOL's mission. So resilience is the ability to continue operating after a given disaster. Then I looked at system security engineering design principles, and the first one was clear abstractions. Clear abstractions mean that the SOL should have a design that is obvious to others, functions that are distinct and well-defined, and information exchanges that are labeled and fully characterized within reason. Ideally, the system design should be easily understandable and seemingly obvious to interpret by an engineer. So that is all about clear abstractions. Number two is least common mechanism. The principle of least common mechanism seeks to reduce unnecessary duplication within the SOL. More specifically, if multiple components in a system require the same functionality, the desired functionality should be built into a single mechanism, in brackets physical or logical. This reduces complexity across the SOL, as well as reduce errors of omission and commission, which may introduce vulnerabilities. The third principle is modularity and layering. Modularity organizes and isolates functionality and related data into a well-defined conceptual groupings, whereas layering orders the relationship between these groupings and their associated data flows. Layering implies an ordered hierarchy of groupings, system elements, or objects. Modularity implies plug and play of the groupings with the hierarchy. And then the fourth principle is ordered dependencies, in brackets partially, refers to the logical or hierarchical arrangement of the system elements. The elements are layers, modules, objects, etc., and specifically an ordering with functional calls. Synchronization and other dependencies are achieved through linearization or hierarchical design. Partially ordered dependencies simply refers to when the ordered dependency is mostly hierarchical, but may require an additional non-hierarchical linkage. Ordered dependencies also seeks to minimize or ideally remove structural dependencies. Logically structuring dependencies and minimizing them where possible contributes to isolation between layers, increases understability of the design, reduces system complexity, and facilitates testing and analysis. The 15th principle is efficiently mediated access, which ensures security mechanisms do not hinder system performance to an acceptable level. This principle seeks to optimize security and performance trade-offs such that stakeholder systems, secure requirements or goals are met while the SOL performs its mission-critical functionality. Number 6 is minimized sharing, which states that no resources should be shared between system components unless it is absolutely necessary to do so. This principle directly supports the access control and isolation strategies by reducing the number of interactions between various elements. The 7th principle is reduced complexity, which implies that the system design should be as simple and small as possible. This reduces total life cycle costs and has several benefits, especially when considering the development of secure systems. Number 8, secure evolvability, which implies that a system be developed to facilitate upgrades and maintenance activities in a secure fashion. This means that the SOL should be designed to easily and securely adapt to changes in its configuration, functionality, architecture, structure, interfaces, and interconnections. Trusted components elements implies that it is another principle, which is number 9. Trusted components implies that a component must be at least as trustworthy as the components it supports, and that is the system element, must be trustworthy to at least a level commensurate with the security dependencies it supports. Trusted components and specifically the resulting trustworthy behaviors enable the development of trustworthy, secure systems such that desirable levels of trustworthiness can be achieved through a systemic approach. Hierarchical trust provides a logical basis for reasoning about levels of trustworthiness when developing a system from several components within the context of NIST SP 800-160. Hierarchical trust supports the strategy of access control and, to a lesser extent, resilience, hence justifying trustworthiness of decisions. The other principle is commensurate protection, which implies that the degree of protection provided for a component must be appropriate to its desired level of trustworthiness. For example, as the trust placed in a component increases, the protection against unauthorized modification of said component should increase to the same degree. This principle is consistent with the historical security defense approaches in that the most valuable item should be very well protected. Hierarchical protection means, it is another principle, that the component needs not to be protected from more trustworthy components. It addresses the aspect of unnecessarily overprotecting a component. This principle supports all of the security strategies to varying degrees by protecting the SOL from components, functions, data, and even users with lower trustworthiness, and reserving higher level privileges for more trusted entities. 13 is minimize the trusted components, which implies that a system should not have very many trusted elements, components, data, or functions. It suggests that SOL should contain a few trustworthy components as possible. Thus, this principle directly impacts multiple facets of system development and total life cycle costs. Minimizing the number of trusted components helps to mitigate the impact of those compromises, lowers assurance costs, and facilitates easier monitoring of a system's security posture. 14 is least privilege, which implies that a component should be allocated sufficient privileges to accomplish its specified function, and no more when often described with respect to system users. When employed at the systems level, the principle is much more widely applicable to each system element, component, network, or user. Then the other 15 is multi-factor permissions. This requires that multiple authorizing entities or operators provide consent before a critical operation occurs. While traditionally thought of as two operators turning a key or offering a password, this principle should include authorization through multiple means to include human and system. Mostly commonly, multi-factor permission is granted through successive approval action, i.e. sequence of events occurring without error. This principle directly contributes to access control, strategy, and defense in depth, while also enhancing survivability by protecting mission-critical information, components, and processes. 16 is self-reliance, which means that systems and all elements, to include information and software, should minimize their reliance on other systems, elements, or components. While this principle is specifically targeted at building trustworthiness, it is generally applicable for protecting the SOL as well as applying the self-resilience principle can significantly reduce design and implementation complexity, increase testability, and improve system survivability. This principle directly impacts the isolation strategy by minimizing both external and internal dependencies. 17 is secure composition, which means that a combination of system elements designed to enforce a security policy should result in a system that enforces said policy at least as well as the individual components do. 18 is trusted communication, means that each communication channel, i.e. an interface, link, or network, must be trustworthy to a level commensurate with the security dependencies it supports. While seemingly redundant, this principle specifically considers the necessary protections for the SOL's communication links and ensures weaknesses are not introduced via communication channels. This is important because communication channels are inherently more susceptible than the SOL's internal elements. So here I came to a conclusion that, in summary, the article introduces the need for system security engineering, defines key concepts in the topic, talks about strategies in system security engineering, and then principles it follows. The aim is to assist developers, owners, and operators in undertaking, understanding, and achieving a rigorous yet cost-effective system security engineering approach. This work uniquely provides an analysis of NIST SP 800-160 Volume 1 Security Design Principles with a detailed mapping and analysis of conceptual security strategies to design principles that can be more efficiently designed for built-in and tested to meet security and resilience objectives. Insights regarding the interrelationships among the 18 design principles are described along with practical guidance on when and how they can be applied to more effectively perform system security activities.